Today on Macaulay Math, we're finding the trigonometric form of complex numbers. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus Lesson 33 on the trigonometric form of complex numbers. Our goals for today. We're going to find the absolute value of complex numbers. We're going to write the trigonometric forms of complex numbers. We're going to multiply and divide complex numbers written in trigonometric form. We're going to use De Moivre's theorem to find powers of complex numbers. And then we're going to find nth roots of complex numbers. In this lesson, familiar techniques from earlier on in the course will be used to find the absolute value of a complex number and the trigonometric forms of complex numbers. Since the complex plane uses the horizontal axis for real numbers and the vertical axis for imaginary numbers, techniques like the distance formula and simple sine, cosine, and tangent functions can be used to find absolute values and trigonometric forms of complex numbers. Let's get started.
Okay, let's start with a definition. The absolute value of a complex number, and we'll denote the complex number z as a plus bi, that is your standard form of a complex number, is the absolute value of z is equal to the absolute value of a plus bi, which would be equal to the square root of a squared plus b squared. And we've seen this a couple of times during this course, but I do want to make a note, and this is just something that I see over and over as an error. When you do the absolute value of a complex number, the imaginary unit is not part of that formula. So there's no I that you plug in. You're only plugging in the coefficient to the imaginary part there for b. And so if you go back to your Algebra 2 class, absolute value was defined as the distance along the number line to 0. And the absolute value of an imaginary number is similar to that in the fact that in the complex plane, the absolute value is the distance from the origin to the point in the complex plane. Now I have an xy axis here. That really isn't correct. So let's call this the real axis along the horizontal, and then along the vertical, we will call that the imaginary axis. So if I were to plot the point 3 minus 4i, well, here is 3, and here 1, 2, 3, 4, right there's negative 4. So the complex number, so if I put the complex number right here and call this 3 minus 4i, then the absolute value is just this distance right there, which makes it similar to what we had for the absolute value of just a real number. And that is why it looks like that Pythagorean theorem like we've seen in a number of instances. So let's calculate this. The absolute value of 3 plus 4i is going to be equal to the square root of 3 squared plus 4 squared. 3 squared is 9. 4 squared is 16, 9 and 16 is 25, the square root of 25 is 5, so that is the absolute value of that imaginary number. Second definition, the trigonometric form of complex numbers. So if z is equal to the complex number a plus bi, then the trigonometric form will be z is equal to r times the cosine of theta plus I times the sine of theta, where a is r times the cosine of theta. So this a is r cosine theta, and this b is r sine theta, and r is the absolute value of that trigonometric function, and the tangent of theta is equal to b over a. The number r is called the modulus. It's also the absolute value, and theta is called the argument of z. All right. The product and the quotient of two complex numbers. So let z1 be r times cosine of theta 1 plus I times the sine of theta 1, and z2 be r2 times the cosine of theta 2 plus I sine theta 2. Be two complex numbers, then the product z1 times z2 will be r1 times r2 times the quantity of cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. the quotient of those two numbers. If I'm dividing, divide the r's, and then instead of adding the thetas, we're going to subtract the thetas. And then de Moivre's theorem, if z is equal to r times the quantity cosine theta plus I sine theta, which is a complex number, and n is a positive integer, then z to the nth power is equal to r times cosine theta plus I sine theta, all to the nth power. And then that will be equal to, when I bring this down, it'll be r to the nth times cosine of n theta plus I sine n theta. Now, this is just an extension of this product rule. So when I multiply r by itself n times, I'll just be multiplying these together n times, hence r to the nth. And then I would add the same theta to itself n times, which would be n theta. So these two are related. Next definition, complex number u equals a plus bi is an nth root of the complex number z if z is equal to u to the n, which would be equal to a plus bi to the nth power. The nth roots of a complex number. So this is just a formula to calculate the nth roots of a complex number. Now, if we said what is the third root of 27, you'll remember that that is 3. In the complex plane, though, any number, whether it be a full real number or a complex number, has n number of roots in it. And so in the real number system, the third root of 27 is 3, but in the complex number system, 27 would have 3 complex roots. And the way that you calculate those, so if I start with z is equal to r times cosine theta plus I sine theta, has exactly n distinct nth roots given by, you take the nth root of whatever that modulus is, and then you take the cosine and you plug it into this expression here. So you go theta plus 2 pi k divided by n, and these n's match up. And then k, the way you calculate k, you start with 0, and then you go 0, 1, 2, 3, all the way up to n minus 1. And since you're counting with 0 instead of you're counting with 1, when you go 0, 1, 2, 3, you still have your n different roots. All right, so as an example, let's find the standard form of the complex number. So what this question is actually asking you to do is to take this trigonometric form and then change it into a plus bi form. And that's not too crazy difficult for us to do, because both the cosine of 5 pi over 6 and the sine of 5 pi over 6, 5 pi over 6 is on the unit circle, and since we did such a good job of memorizing the unit circle, we can do that part in our head. So we'll go 6 equals, so 5 pi over 6, the cosine of 5 pi over 6 is square root of 3 over 2. And we'll have my I, and then the sine of 5 pi over 6, well, that is negative 1/2. All right, so now we'll distribute this 6. So 6 times square root of 3 over 2, I'll get a 2 to cancel out from the 6 and the 2. That'll leave me with 3. And so 3 times square root of 3 is 3 square root of 3. And then 6 times negative half will be negative 3. Negative 3 times I will be negative 3i. And that is in a plus bi form, even though I have a square root there. So we will put a box around that, and we will say we are done. All right. We have 2 examples here where it asks us to do a multiplication and a division. So we will relate back to the rules that tell us how to multiply. If I am multiplying 2 complex numbers in trigonometric form, I'm going to multiply the modulus, and then I will add the arguments. So we'll come back, and so I'm going to multiply the modulus. So I'll go 4 times 5, and then we'll go the cosine of pi over 12 plus 7 pi over 12, and that will be plus I sine of pi over 12 plus 7 pi over 12. And since the denominators are equal, that'll be easy to simplify. 4 times 5 is 20, And then I get 1 pi over 12 plus 7 pi over 12 gives me 8 pi over 12. And I can take a 4 out of both of those. So I'll have the cosine of 2 pi over 3 plus I sine of 2 pi over 3. And that is my answer. So similarly, when they ask us to divide two complex numbers in trigonometric form, we will divide the modulus. And so we will go 2 divided by 4, and then we will subtract the argument. And so I'll have the cosine of 120 minus 40 plus I sine 120 minus 40. And 2 divided by 4 is a half. And then cosine 120 minus 40 is 80. And I can't simplify anything else, so that is our final answer. Next example, it says use de Moivre's theorem to find. So here we're going to raise these to a power, and if we go back up and look at de Moivre's theorem, that means if I take the complex number and I raise it to a power, I will raise the modulus to a power, and then I will multiply that power times the argument. So let's go and do that. So we're going 3 times the cosine of 150 plus I sine 150 raised to the 4th power. That'll give me 3 to the 4th power times cosine of 4 times 150 plus I sine of 4 times 150. All right. Now, 3 to the 4th is pretty easy. It's just 81. Now, 4 times 150. Well, 4 times 150 turns out to be 600. Now, 600 is technically outside that unit circle. All right? So, if we think about it, in terms of the unit circle, if I start here and I go around one time, that'll be 360 degrees. If I go around a full second time, that would be actually 720 degrees. So we're not actually going all the way around another time, okay? In fact, if we come down to here, we'll be about to that 600 degrees. And so what we'll do, we're going to find a reference angle that's a better solution that's on the unit circle. So what I'll do is, since it doesn't go around twice, I'm just going to subtract 360. Now, if it was bigger than 720, I would subtract away 720 to get my reference angle that I'm going to use. And so you're just going to be subtracting away multiples of 360 or multiples of 2 pi to get to something that is on the unit circle between 0 and 360 degrees. So we'll have 81, and I should have equals at each of these. So we'll have the cosine of 600 minus 360 plus I sine of 600 minus 360. And that'll give me a final answer of 81, and then 600 minus 360 is 240 degrees, so we'll go cosine 240, and since our final answer, we'll put degrees in there, and I sine of 240, we'll put degrees in there, put a box around that one, and say that we are finished. Okay, next example, it says find the square roots of 16 times the cosine of 60 degrees plus I sine of 60 degrees. All right, so finding the nth roots, we're going to use that formula that they gave us earlier on in the lesson, and we are going to use this expression right here. So we're going to go the nth root of cosine, 0 plus 2 pi k over n plus I sine theta plus 2 pi k over n, where k is equal to 0, 1, 2, 3. Now, since we're doing square roots on this one, n is actually only 2, so we only are going to need to do this twice. Our k value will only be 0 and 1, because if n is 2, n minus 1 would be just 1. That tells us we stop there. Now, if they were asking for the third roots, you'd go 0, 1, and then 2, because that would give you 3 values for k, because it's the third root. All right, and so to make this a little easier on poor old Mr. McCulley, let's just copy this and bring it over to here, and we will paste that in so that we can see that. And since they want square roots, we'll go n is equal to 2, and that means k, again, will be 0 and 1. So our first square root of this imaginary number will be the square root of 16, comma, the cosine of theta, which in this case is 60, plus, let's convert that 2 pi to 360 degrees, and then k over 2 plus I sine of 60 plus 360 k all over 2. So our first one, the square root of 16 is going to be 4, and then we'll plug in 0 for k. So I will have the cosine of 60 plus 360 times 0 all over 2 plus I sine 60 plus 360 times 0 all over 2. And then my second square root will be, again, 4, and then I'm going to try and fit this in here. It'll be the cosine of 60 plus 360 times, now k equal to 1 all over 2, and then it will be plus I sine 60 plus 360 times 1 all over 2. And let's see, let's reduce this. So I'll have 4 cosine 360 times 0 is 0 plus 60 is 60 divided by 2 is 30. And that's our first one. And then our second one will still be a 4 there. And then I'll have cosine, let's see here, 60 and 360 will be 420. 420 divided by 2 will be 210. Now 210 is on the unit circle, so I can leave it. And then I'll have the same value for sine. Put degrees on all of these things. And that will be my final answer. All right there, folks. That's all I have for today. So, the Star Wars fun fact of the day. Darth Vader is the big bad of Star Wars Episode 4, A New Hope. But he only has 12 minutes of screen time in the whole 2 hours and 30 minutes. That's not a whole lot, but he uses that time well to make a big impression. All right there, folks. That's all I got for today. You have a great day. Goodbye.